In this video, we'll continue our discussion of planes in 3 space with an example talking about finding the equation of the line of the intersection of two planes. Okay, so we were given two planes at P1, P2. I drew a picture of this because, again, a picture is going to make this much easier for us. We are trying to find the equation of the line right there, where they intersect. We're going to use the information to come up with what we need. That's where I start every time. So let's write our need list. Okay, need for a line is we need a point and we need a directional vector that points in the direction of the line. Okay, so let's start thinking through this. I know P2, which is my orange plane, it has a normal vector, and I'm going to draw it going up this other one. All right, so there is my normal vector. I know it meets at a 90-degree angle, and this is going to be my N2, my normal for my second one. Okay, we can also do the same thing right here for N1, and that also creates a 90-degree angle. Now, we can get a point from this. We're going to have to try to find one. Let's do our directional vector first. All right, so if I'm wanting a vector that describes this line in this direction, and it's actually even just put it right there where we're probably going to grab it from. That is my directional vector for my line. Well, as you can notice, we have a relationship there between N1, N2, and V. N1 and N2, those may not be orthogonal to each other, N1 and N2, but we do know that V is orthogonal to both N1 and N2. And since the lines are set up the way they are, the cross product there would give us an orthogonal vector to N1 and N2, which actually runs in the direction of the line. So to find my vector, we are just going to find the cross product of N1 and N2. So V is equal to N1 crossed with N2. Right, so we need to write down those vectors. So let's do that. We'll do N1 first. Let's go ahead and drop this down. Oops. All right, so N1, if I grab that from P1, I got 3, -1, 2. If I grab now N2, N2 is 4, 3, -1. Let's grab the coefficients. Right, now we can go ahead and set up our cross. So I got I, J, K, and then I got 3, -1, 2, 4, 3, -1. Okay, let's set this up. I'm going to go down to have more room. Cover up our I column, write down the rest. I minus, cover up the J column, write down the rest. That's J. Plus, and then cover up the K column, write down the rest. And that is K. All right, so I use my normal determinant now. I got 1 minus 6. My normal, my 2 by 2, nothing normal. -3 minus 8, J. And then 9 plus 4, K. So this vector ends up being -5. That's a -11, but it's going to be +11 now, and then 13. So that vector is orthogonal to both. Now, we just need a point that ends up being on there. So we need to find a point and come up with like a system of equations. So how we're going to do that, all right, so there's my directional vector. We have that. I'm going to go ahead and highlight that. You know to use it. All right, and then let's do our point. So to do a point, we're going to set x or y or z equal to 0 in system of planes. What I mean by system of planes is the two planes given. So in this problem, let's let x equal 0 and see where that takes us. All right, so I'm going to zoom out so I can see my planes. All right, so my plane there is at the top. I'm going to write these down and then I'll zoom back in. All right, sorry about that. I am going to rewrite these in better handwriting for note's sake. Sorry about that. 3 times 0 minus y plus, that's not much better, 2z equals 3, at least it's smaller. 4 times 0 plus 3y minus z equals negative 5. All right, so now we're going to work those. Now we have a system of equations, two unknowns. So we're going to take those. So we got negative y plus 2z equals 3. And then I got 3y minus z equals negative 5. I'm just going to solve this one for y. Y equals 2z minus 3. We could plug that into the other one. 3 times 2z minus 3 minus z equals negative 5. So if I work all that out, I got 6z minus 9 minus z equals negative 5. So I got 5z. Add 9 to the other side, I got 4. So I got z equals 4 over 5. I can now take this and plug it into the y equation. So y equals, sorry, it's going to be kind of weird working to the left. 2 times 4/5 minus 3. I'm just going to use a calculator. I'm feeling lazy. I got negative 7 over 5. And x was 0. So we actually have the point 0, negative 7/5, 4/5. So this was our point. Right? And then we're going to write our parametric equations for our answer. Parametric EQs. So x equals, I use the point, which is 0, plus the negative 5t. Y is going to be the point, negative 7/5, plus 11t. And then z is going to be 13 plus 4/5. Oh, I got them backwards. Be careful not to do that. It's very easy to do that. The point first, 4/5 plus 13t. There we go. So this is our answer here at the end. Parametric equations. We could have done also symmetric if we wanted to, but parametric suffices in this problem. So what we did, let's recap. Going back up, we have two planes that intersect. I can find the normals of those planes. If I cross the normals, I get an orthogonal vector that actually describes the line of intersection. I use that orthogonal vector. That's what's highlighted here. That's going to be my directional vector for my line. To get the point, because they didn't give us a point, we set x, y, or z, and this is going to create a system of planes within that line. We can do that. We get two equations, two unknowns over here. We solved for z. We took z and we plugged it back in to get y, and then we knew x was 0 from the very beginning. That's what we chose to do that. Right. This one's a bit tricky, can be a bit tricky. Just try to follow your nose with I think the normal vector makes sense. The point is the tricky part.